Okay, hello everyone. If you received my message, we did not have class today. I'm actually in my vehicle right now, writing out the notes. So, you have to stay productive wherever you are. My car is in park. I'm not riding and driving. And so, these are the notes. This is the conclusion of section 7.6, dealing with improper integrals. Make sure you go back over the notes from yesterday, the homework, and also make sure you go back in the book. I know some of you all don't read the book, but especially you need to read the book for each section, especially if you're struggling and having trouble in this class. You need to read the book along with my notes. My notes are not the end all be all. You need to look at the book, look at their examples. Sometimes I do the same examples, but a lot of times I like to do different examples because I want you to see many examples of the same problem. So I won't do the same examples. But anyway, we're finishing up section 7.6 with the second case of improper integrals. We talked about the first case yesterday, and so now we're going to talk about the second case and conclude because we're moving on to chapter 10 tomorrow. Okay, and so sometimes we talked about yesterday when the integrals have infinity, if they're unbounded, so positive or negative infinity. However, we also may need to integrate over an interval, let's AB, so we actually have an interval of finite numbers where the function, or real numbers I should say, where the function has a discontinuity. And in other words, if you remember from Calc 1, that means there's a vertical asymptote involved. Okay. So in example 1, we're going to find the area under the curve. And for this function here, y equals 1 over the square root of x above 0, 1. Okay. So I drew a picture so we can get an idea what's going on. And as you can see from the picture, there's a vertical asymptote at x equals 0. Okay. And so remember that. So that's where our function is undefined. Okay. So that means, so just note that 1 over root x has a vertical asymptote at 0. Okay. So we need to look at the limit then. So wherever if it's infinity, meaning there's no finite number, or if it's a point where there's a discontinuity, then we need to look at the limit as that point is approaching, depending upon what we're talking about. So actually, when we look at the limit, notice in this function that we want from, okay, so like I said, I'm in traffic, and that was some noise. Okay, so that means we're going to take, so let's see, so note, and what we're trying to evaluate, we want a between 0 and 1, right? So that means we need to compute the integral from a to 1 of 1 over the square root of x dx, since that's where our bad point is. Okay. Okay, so that means we can rewrite, so the integral from 0 to 1 of 1 over square root of x dx equals the limit as a approaches 0. And looking at that picture, and the interval we're talking about is the closed interval 0, 1. So we only care about a from the right. You guys remember that notation from Calc 1 of the integral a to 1 of 1 over square root of x dx. And once you do that integration, so I'll leave that to you, for you all to integrate, you should get the limit as a approaches 0 from the right of 2x to the 1/2, evaluated from a to 1. All right, so that equals the limit as a approaches 0 from the right of 2 times 1 to the 1/2, or you could just write it as square root, minus 2 times a to the 1/2. Okay. And that equals, and so now we can actually, you can either break, well, we could break this up to as the limit as a approaches 0 from the right of, well, 1 to the 1/2 is just going to give us 1. So that's just going to be 2 minus the limit as a goes from 0 to the right of 2 to the root a. Let's just put that. And so we know by properties of limit that first term is just going to give us 2 minus, well, now it's just the square root, right? So it's 0 from the right. The limit is a approaches 0 from the right. So that's just going to give us 0. So our final answer is 2, which tells us that our integral converges. Okay. So now just some definitions. So you might want to pause and then write this down because I'm just going to go over it fairly quickly. So let f be a continuous function, all right, on AB, except at the endpoint A. If the limit as x approaches a from the right of the integral from a to b of f of x dx equals L, where L is finite, that's finite right there. We say that the integral from a to b of f of x dx equals L, and the integral converges. Okay, so that's our first definition, and then we have the second definition. If f is continuous on AB except at endpoint B, and the limit as x approaches B from the left, the limit as x approaches B from the left of the integral a to b f of x dx equals L, then L is finite, and we say that the integral from a to b equals L, and the integral, okay, I keep getting interval and crow, okay. I digress. All right, integral converges. Otherwise, the integral is divergent. Okay, so that's that terminology. And then the last definition, if f has a discontinuity at C, and so C is some number between A and B, then when you have the integral from A to B of f of x dx, you have to break it up according to that discontinuous point C. And so you'll break it up into the integral from a to c of f of x dx plus the integral from c to b of f of x dx. And this, which is very important to note, this will converge if both converge. Okay, both have to converge in order for the entire integral to converge. Okay, and so let's look at this example here. So we have the integral from -1 to 1 of 1 over x to the 4/3 dx. So pay attention to this note, and it's a very important note that you should keep in mind. You always, when you're dealing with improper integrals or integrals in general, because actually now I could throw this type of integral in with all the other integrals and tell you to use any technique. Although I don't know if I would do that. I'll think about what I do that. Just keep in mind when you're dealing with these problems, improper integral in this section, and when you're dealing with this homework, that if you have an integral where there's no positive or negative infinity, and at the endpoints, the function is defined, because at -1 and 1, this function is defined, right? If that's the case, then you know, well, there's some point in between that interval. Now we're talking about intervals. In between the interval -1, 1, where this function is discontinuous. And in fact, you guys probably see it, 0 is discontinuous. So that means we're going to have the integral from -1 to 1 of 1 over x to the 4/3 dx equals the integral from -1 to 0 of 1 over x to the 4/3 dx plus the interval from 0 to 1 of 1 over x to the 4/3 dx. Okay, so I just rewrote from the last slide the right-hand side just for sake of space on the board, but you should keep it aligned on your paper. And so again, we have the integral from -1 to 0 of x to the -4/3 dx plus the integral from 0 to 1 of x to the -4/3 dx. And that equals the limit as b approaches 0 from the left. So notice from this side, we're looking from -1 to 0, right? So I'm just going to put, so that's from -1 to 0, which means you're looking at 0 from the left. So you're looking at the negative values really, really close to 0. And then so the limit as b approaches 0 from the left of -1 to b of x to the -4/3 dx, plus the limit as a approaches 0 from the right, because now we're looking at the interval 0 to 1. So the limit as a approaches 0 from the right of the integral a to 1 x to the -4/3 dx. And again, I'll leave it to you all. So if you want, you can stop the video and then do the integral sort of side work to make sure that you all get that for your antiderivative. And so now, so this equals the limit as b approaches 0 from the left of -3 over x to the 1/3, and that's being evaluated from -1 to b, plus the limit as a approaches 0 from the right of -3 over x to the 1/3, and a evaluated from a to 1. I will say this, I'm not a stickler on, you see, knowing where the a and the b. If you want, you can keep it as r, like we used in class yesterday. You can keep it as r approach, as long as you're approaching the right number, and from which, if it's a one-sided limit, you know that's correct. So in all honesty, if you were to put r as r approaches 0 from the left, as r approaches 0 from the right, as long as you understand that you're taking those two integrals and it means something different for each of those, I'm okay. So you won't get confused, because I remember some students getting confused over, oh, when do I put the b and when do I put the a? It's not really a big deal. The heart of it is knowing what to evaluate it from. Okay. And so now what's nice about this, so although it's two integrals that we need to evaluate, what's nice is that I would advise you all to evaluate it one at a time, because remember from the definition, I believe, if one diverges, then the whole thing diverges. So you might save yourself some work if, and we'll see in a minute when we evaluate this, if that diverges, then we don't need to check the other thing because the entire thing diverges. Now, if it converges, that means we do need to check the other, we need to check this to see what's going to happen with that. But I would say evaluate it one at a time, just so you can save your time, possibly some time. Okay. And so this is equal to the limit. So I'm just going to take this first one. And so maybe I should take the equal sign off, because I just want to evaluate that first part. The limit as b approaches 0 from the left of -3 over b to the 1/3 minus -3 over 1 to the 1/3. I guess I can put another parenthesis there. Okay, and so that equals the limit. And this part that I'm writing here, you actually don't need to write this part either. If you can do this in your head, if you can just see where it's going in your head, I'm okay with that too. And so this is going to be 3, right? It's just going to be 3. Okay. Now, I think I briefly talked about it yesterday, but this is b approaches 0 from the left. So you have -3 over a really, really small number. This is a really, really small number. So a number over a really, really small number will blow up, right? And so, in fact, this will go off into infinity. And so we can say, and I'm sorry, I'm just trying to save space. I don't want to start a new slide. And we could say, thus, the entire integral diverges. And sorry, I didn't want to add a new space. We're going to do another example, but I'm going to stop this video and do another video, because if it goes past 15 minutes, sometimes it doesn't load properly.